This video demonstrates how hashing functions are used in common data structures like hash tables and hash sets. Hash tables or hash sets are a type of data structure in which the index value of the data element is generated from a hash function. This enables very fast data access as the index value behaves as a key to directly locate the corresponding value. We will use a set of values as an example. However, the same concept applies to the hash tables as well. Consider a set of data as follows. Each data is passed through the hash function, which computes an index, and the element is then stored at that index. This approach enables the fast retrieval because there is no need to search through the data sequentially, which would take big O of n time. Instead, the hash function provides a direct lookup of the index, reducing the time complexity of accessing a value to big O of 1. However, collisions may occur when two different data elements are mapped to the same index, which can increase the time complexity to big O of n in the worst case. The hash function is denoted as fx, which can vary depending on the data type being stored in the hash table. A hashing function is a function that takes a data element and returns an index where the data should be inserted. It typically lies within the range of 0 to size -1, where size is the size of the hash table or hash set. The specific hash function can vary based on the type of the data being stored. For example, for numbers, a common hash function is data element modulus size, which returns the remainder that acts as an index to store the data element. Here, size is referring to the size of the hash set or hash table. For strings, one approach is to convert each character to its ASCII value, sum these values, and then take the result modulus with the tables or the map size to determine the index. When a hash collision occurs where two elements map to the same index, it can be resolved using various techniques such as open addressing, which involves searching for an open slot and can be done using methods like linear proving, quadratic proving, double hashing, or separate chaining, where multiple elements at the same index are stored in a linked list or another structure. Let us continue our discussion with open addressing collision handling. In open addressing, data elements are stored directly in the hash table by searching for an open or vacant slot when a collision occurs. Let us start with the first technique, that is linear proving. In this method, the next available position is searched sequentially within the hash table. Mathematically, the new position is calculated as hash of the data element plus I modulus size, where I is the ith iteration after the collision happened. Let us consider the data and try to insert in the hash set using the hash method. After a collision happened, the function calculates the next slot, which is nothing but the position next to the collision. This process continues until an empty slot is found. Let us move to the next method, that is quadratic proving. In quadratic proving, the search for the next available slot follows a quadratic pattern. The new position is calculated as hash of the data element plus I square modulus size, where I is the ith iteration. Let us consider the same data and try to fill up the data element for which collision was happened. After the collision happened, the formula for the first iteration is index equals to 1 plus I square modulus 10, where 1 is the hash for the data element 91 for which collision was happened, which evaluates to index 2. Again, this process continues until an empty slot found. For the iteration 2, index can be calculated as 1 plus I square modulus 10. Here I equals to 2, that is the second iteration, and hash for the 91 remains 1. This calculates as fifth index. Again, for the fifth index, we have collision. This process continues for the iteration 3. Index for the iteration 3 can be calculated as 1 plus I square modulus 10, which evaluates to index 0. Quadratic proving avoids the clustering problem which can be seen in linear proving. Next technique is double hashing. Double hashing uses a second hash function to calculate the next available slot. The new position is calculated as hash for the data element plus I multiply hash for the data element again. This hash function can be a same hash function or can be a totally different hash function. Modulus size, where I is again the ith iteration. For the simplicity, consider the same hash function is being used. 91 is the data element for which the collision happened. Let us try to fill this data element after the collision using the double hashing technique. For the first iteration, the index can be calculated as 1 plus I multiply 1 modulus 10, which evaluates to index 2. Again, for the index 2, we have a collision. Thus, move to the next iteration. For the iteration 2, index can be calculated as 1 plus I multiply 1 modulus 10. Here I equals 2, that is the iteration count, which evaluates to 3. And we found the empty slot after this iteration. This method provides a more distributed proving sequence compared to linear and quadratic proving. In all these strategies, the function continues to probe for an open slot until a vacancy is found. Let us continue our discussion with separate chaining collision handling. In separate chaining, when a collision occurs, multiple data elements that hash to the same index are stored in the same slot using a linked list or another structure like dynamic array or a balanced tree. Let us consider the same data, pass it through the hash function and insert it into the hash set. After a collision occurred, the new data is simply added to the chain at that index, typically at the head or the tail of the linked list. This allows multiple elements to coexist at the same index while maintaining efficient lookup, insertion, and deletion operation within the chain. At the last, let us revisit the properties of hash function which hash table utilizes. The first property, which is same input should always produce the same digest. Second, it is difficult to produce a given digest. Third, algorithms should be efficient enough to process data quickly. Thank you for watching. I hope you enjoyed the video and I will see you in the next one.